So let us continue lecture 5. In this video of lecture 5, we are going to study linear density. Linear density is defined by that formula, and it is simply number of atoms contained on a direction vector divided by length of that direction vector. For calculations, the items are regarded as circles, and while counting number of atoms in the numerator of the formula, sharing of that atom must also be considered. What is the meaning of this is that if let's say we consider this direction as shown by the right arrow, then there are actually three atoms whose center lie on this direction x, y and z. But as we already know that the corner item, so this corner item and this corner atom, so these corner items are shared with the adjacent unit cells. So as we are considering them as circle, I can say only half of atom X and half of atom Z lie inside this unit cell under consideration. Okay. So while counting the number of items on this particular direction, we are going to consider equivalent number of items. That means I can say that half of this is inside the unit cell, half of this atom is inside the unit cell, and atom Y is completely inside the unit cell. Hence, the total number of items contained on that direction vector is half plus half plus 1. So, which is equals to 2. So, that's how we count the number of items contained on a direction vector. Then, so let us calculate linear density in 100 direction of FCC unit cell. So 100 direction inside FCC unit cell is shown in this picture. Now we need to calculate the numerator, which is number of atoms contained on a direction vector. Okay, so let me draw this direction vector. So this is the direction vector. So if you look at that direction vector from side, that's what it appears to be. And on each of its end, there is an item. Okay, so this item corresponds to that, and this item corresponds to this. Okay, now only half of those items is inside this unit cell under consideration, while the other half is shared and contained by the adjoining or adjacent or neighboring unit cell. Okay, so that means half of this and half of this. So equivalent number of items become 1. So half of this, half of that. So those are the number of items contained on the direction vector 100, and length of that direction vector is equals to the lattice parameter. So this direction as indicated in this picture is A. So that much length is equals to the lattice parameter A. So in terms of lattice parameter it is A. So this becomes 1 upon A, that is in terms of lattice parameter. In terms of atomic radius r, we have already derived an expression between A, lattice parameters A, and atomic radius r, which is for FCC is 2r root 2. Okay, where capital R is the atomic radius. So this is the expression for linear density in 100 direction of FCC, 1 upon 2r root 2 in terms of atomic radius r. Okay. Let us now calculate the linear density in direction 111 of FCC. So this direction is shown here in this picture, and it's basically the diagonal of this cube. And so again, the number of atoms contained on a direction vector remains same because we have two corner items at each end of that direction. So that becomes half, because half of them is shared by the adjoining unit cell. So half. And the main task here is to find out the length of this vector. and as you can see that there is a hypotenuse, that direction is a hypotenuse of the right angle triangle whose other two sides are x and y. Okay, so I can write this, the direction or the length of the direction vector can be found out by this formula. Applying Pythagoras theorem to that right angle triangle, this hypotenuse is the direction under consideration equals to half plus half is 1 divided by, if you look at x, then here in the picture above you can see that the corner items touch each other along the face, and hence x is 4r. So x is 4r because all the faces will have same configuration. So 4r whole squared, x is 4r, plus y is the is equals to the lattice parameter a, and we know that a is 2r root 2 whole square. Okay, so this becomes 1 upon under the square root. So 1 upon 4r square inside the square root should be the square of 4r is 16r squared plus square of 2 is 4. So 4 and square of root 2 is 2. 4 into 2 is 8. Becomes 8r squared. So this is equals to 1 upon 16r squared plus 8r squared is 24r squared. So this becomes equals to 2r root 6. So that's the modification. So this is the expression for linear density in 111 direction of FCC unit cell. So let us solve an example based on linear density. Atomic radius of copper is 128 nanometer. So this is the capital R, and copper has FCC crystal structure. Find linear density of copper in 100 direction. Okay. So we already know, we already derived an expression for linear density of FCC crystal structure in 100 direction, which is given by this formula. And as copper has FCC crystal structure, we can use this formula to find out the linear density in 100 direction. All we have to do is substitute the value of R in this expression, which comes out to be 1 upon 2 into 0.128 into 2 equals to. So if you calculate this, this comes out to be 2.76 nanometer inverse. So this is the unit of linear density, nanometer inverse, or in terms of meters it would be 2.76 into 10 raised to 9 meter inverse. Okay, so this is how we compute the linear density. For calculating linear density, you must know what crystal structure a particular element has.